We're going to take quite a turn here in solving differential equations and look at solving them by the use of operators. Now, an operator is sort of like a function, but what it does, it operates on a function and turns it into a different function. Now, the particular kind that we're interested in are called linear operators. They're the simplest kind, and a linear operator has two specific properties, which I'll outline in a moment. But linear operators crop up in a lot of areas of advanced mathematics and are very, very useful for solving problems. You'll run into an idea like this called linear transformations in linear algebra, for example. It's a very similar idea. Anyway, a linear operator has two properties. And so the first property says that if the operator, which I'm going to call L, operates on the sum of two functions, u plus v, then it's going to equal to the operator operating on u plus the same operator operating on v. So in other words, it looks like it follows a distributive law. And it's not really the distributive law that we would use in the context of, say, real numbers, but it sort of resembles it. So L parentheses u plus v is L of u plus LV. All right, that's one property of a linear operator. And L, of course, is my operator that I've named. And the other property says that if I operate on a constant times a function, then I get the constant times the operator acting on the function. So there it looks like we can factor out the constant, and I guess you could look at it that way. So L of Cu is equal to C L of U. Constant, in a sense, factors out. All right, well, these two properties define a linear operator. And when you think about it, our derivatives are linear operators. And so, for example, the derivative of f of x plus g of x, we know that there's a theorem that allows us to break this up and call it the derivative of f of x plus the derivative of g of x. And another theorem you learn in early calculus is that the derivative of a constant times a function is simply the constant times the derivative of the function. So that shows that the derivative is a linear operator. And with that in mind, I'm going to let capital D represent a derivative operator. And so capital D means that first derivative operating. Now it may not be d over dx, it depends on what the variable is, but that's the idea, it's the derivative. So let me erase the board and give you some examples here. First off, starting real simply, the differential operator operating on this polynomial, x to the fourth minus 5x cubed plus 6x minus 1, is simply the derivative, 4x cubed minus 15x squared plus 6. Now, if let's carry this a step farther. If I operate on this new function, 4x cubed minus 15x squared plus 6, I get yet another derivative. And of course this would be what, 12x squared minus 30x. All right. Well, I'm going to interpret that as d squared. So in other words, the operator d operating on d of x to the fourth minus 5x cubed plus 6x minus 1 is the second derivative, which I'm going to call d squared. Alright, so because this is what happened up here, we first operated on the function, then we operated on that. So in a sense, we were operating on the operation on the original function, d of d. And let's call that, for convenience, d squared. And so d squared, let's interpret as second derivative. And so this second derivative, we could just cut the chase and say, well, let's see, it's 4x cubed, 12x squared minus 15x squared, minus 30x, and these two will vanish under the second derivative. So we could, I guess, jump from here to here by using d squared if we want. Now, that's kind of neat because it shows that we can think of the differential operator as a sort of polynomial. Let me give you another example. Here I've created a polynomial out of differential operators, d squared minus 3d minus 4, and I want to ask what happens when that operates on a function y. So this polynomial operator, differential operator, operates on y, and it turns out that, and there are theorems that support all this. In fact, if you're using our Morris, Tenenbaum, and Harry Pollard book, you'll find all these theorems are addressed in there, and they're pretty much intuitive based upon all those theorems you see in calculus. In any event, we can write this as d squared operating on y minus 3 times the differential operator operating on y minus 4 times y. So in a sense, there are theorems that would support this distribution of the function throughout the polynomial operator. And you know, if you interpret this as the second derivative minus 3 times the first derivative minus 4 times the function, then that's exactly what you get. You literally can distribute the function throughout this parentheses. All right. Well, this would be y double prime minus 3 times the derivative of y by minus 3y minus y prime. Y double prime minus 3y prime minus 4y. There we go. So if I had this equation, y double prime minus 3y prime minus 4y equals to e to the negative 2x, then I could represent it as d squared minus 3d minus 4 times y operating on y equals to e to the negative 2x. There we go. So here's a way of representing a differential equation in terms of a linear operator, the differential operator. And you might say, well, okay, well, how would we solve this? And you think, well, it's sort of intuitive. Wouldn't I divide? In other words, y would be e to the minus 2x over d squared minus 3d minus 4. Then you got to think, well, what would it mean to divide here? And in one strict sense, it's kind of meaningless. Doesn't mean anything. We can't really literally divide by an operator. However, we can attach a very useful interpretation to this and consider it as an inverse operator. And so I'm going to get into that very soon here. And so if we interpret division as an inverse operator, then this starts to make sense, and we can start to work with it. All right, let me do just a little more erasing here. Using this example as sort of a guideline, I've gone back to our second order linear differential equation with constant coefficients, a2, a1, a0 constants, equals q of x. It's in other words, it's a non-homogeneous equation. And if I let the p of d be the polynomial operator, a2d squared plus a1d plus a0, then I can rewrite this equation in this fashion here. It would be the polynomial operator operating on y equals to q of x. There we go. So down here it's pretty much what we did. The a2, a1, and a0 were 1, negative 3, and negative 4. And this is my polynomial operator here, which I'm starting to call p of d, polynomial of the operator d. And so up here, the polynomial operator, of course, is siphons off this equation, writes it this way. Kind of resembles our characteristic equation, doesn't it? And so this polynomial operator operating on y equals to q of x. So what is our method of solving? We have to figure out how to interpret q of x over p of d. And in a sense, it's the inverse of this polynomial operator acting on q of x is what we want to think about. Alright, so I'm going to erase the board and show you one other thing called the exponential shift theorem that's going to come in handy for us. And then after that we'll start looking at these inverse operators. As I mentioned, before we get into the inverse operators, we want to take a look at a very useful theorem called the exponential shift theorem. So P of D, a polynomial operator, differential operator, operating on a function u times e to the ax, according to the theorem, is equal to e to the ax times the polynomial operator d plus a operating on function u. Right, now that may be a little hard to wrap your head around at the moment, but let me show you a real simple example of this. Let's look at the derivative of, and I'll call it capital D as an operator, the derivative of x e to the 2x. Alright, so and kind of fix that. There we go. So here my polynomial is just simply d, and my function u is x, and then a is equal to 2e to 2x. Alright, well, if you take the derivative, take the derivative of x, you get 1 times e to the 2x, plus we take the derivative of e to the 2x and then multiply it by x, so that ends up being 2x e to the 2x. There we go. Well, we can factor out e to the 2x. That would leave us 1 plus 2x. Okay. Now, according to exponential shift theorem, this should equal to, this one equals to e to the 2x, and then we have the polynomial operator d plus a, so that would be d plus 2, operating on u, which is x. Operating on x, so I'm just going to write x here. Alright, well, that's e to the 2x, and then this is the derivative of x, which is 1, plus 2 times x, plus 2x. There you go. So there's a very simple example of the exponential shift theorem. And now the book proves it by induction, method of induction. If you don't know what induction is, you'd have to read back a few pages, and he explains it. And I think I'll leave the proof off of this, and maybe later I'll do it. But anyway, let's leave it at that for now, and let's look at one more example of this. Well, here's another little more elaborate example. I have a polynomial operator, d squared plus 3d plus 5, and that would be associated with y double prime plus 3y prime plus 5. And it's operating, 5y. It's operating on this function, e to the negative 3x sine 2x. Now, this would mean, to do this by conventional means, we would have to take the second derivative of this, and it's going to get messy because we have product rule from calculus going on, chain rules going on. Second derivative of this plus 3 times the first derivative plus 5 times the function. So that could take a while, and according to the exponential shift theorem, we can look at it this way. This would be e to the negative 3x, factors out, and then we have the polynomial operator of d plus a. Now d plus a would be d minus 3 because a is negative 3. So it's d minus 3. Operating on sine 2x. Okay, now what do we mean here? Well, I'm going to replace d with d minus 3. So this is e to the negative 3x. And we have a mess here. Let me see. D minus 3 squared plus 3 times d minus 3 plus 5 times operating on sine 2x. There we go. And let's work this out. This will be, let's see, d squared minus 6d plus 9 plus 3d minus 9 plus 5. So that's going to be equal to e to the negative 3x. And then when I take this mess here and combine terms, I have d squared. And let's see, negative 6d plus 3d is minus 3d. And then, let's see, the 9's cancel, but I still have plus 5. There we go. So we end up with d squared minus 3d plus 5 operating on sine 2x. I just noticed something really interesting here because, you know, what's the difference here? The the polynomial stayed the same except for that term changed to a negative. Now, that quite sure is a fluke. I guess it happens. It happened here, but you're not going to see that very often. So don't count on this being any kind of reliable pattern. But in any event, this would be easier to work now because now I just take the second derivative of sine 2x. That's not so bad. And I subtract 3 times the derivative of sine 2x. That's not bad. Plus 5 times sine 2x. In fact, it doesn't look bad at all. Let me just work it out. So this would end up being e to the negative 3x. And the second derivative of sine 2x will be minus 4 sine 2x. And then minus 3 times the first derivative. The first derivative is 2 sine 2x times negative 3. That's minus 6 sine 2x. And then plus 5 times sine 2x. So we would end up with negative 10 plus 5 is negative 5 minus 5 e to the negative 3x sine 2x. And I think I screwed up here, didn't I? Oops, got a little carried away. The first derivative is not sine, it's cosine. So, got to fix that. Cosine. Alright. Try that again. So in this case, this will be sine 2x e to the negative 3x times sine 2x minus 6 cosine 2x. There we go. That's better. So anyway, hopefully you get the idea there. That the exponential shift theorem can be a time saver, and it may include could include complex numbers, imaginary numbers. So we'll see all that unfold as we work through some problems. Next, we're going to get into the inverse operators, and we'll explore that area.